In the last lecture, we learnt about the formation of energy bands in solids, and as an example, we studied the energy bands in sodium. Then we distinguished between conduction and valence bands. We found the gap between them called the energy gap or forbidden region, and on the basis of these bands and the forbidden region, we distinguished between conductors, non-conductors and semiconductors. In non-conductors, this band, this energy gap is of the order of 10 electron volts. In semiconductors, this is of the order of 1 electron volt, and in metals or in conductors, they overlap. So, that is how we distinguished between the conductors, non-conductors and semiconductors. And then we saw intrinsic semiconductors. Intrinsic semiconductors means pure semiconductors like pure silicon, and they are almost insulators. We saw that intrinsic semiconductors are almost like insulators. However, if we add suitable impurities in precisely determined small amounts, mark these words, precisely determined small amounts, we determine precisely how much impurity is to be added, and if we do that, then their conductivity can increase manifold. It becomes many times. The process of adding impurities is called doping, and the impurity added is called dopant. Semiconductors with impurities are called extrinsic semiconductors. We had intrinsic semiconductors which were pure semiconductors like pure silicon. If you add impurities, then they become extrinsic semiconductors. Doping of semiconductors is in precisely calculated amounts can enable us to get the material with conduction properties that we may desire. See, that is what I have said, in precisely determined amounts. So, we can add impurities and then we can control the conductivity. It is this possibility of being able to control the conduction of a semiconductor that has made it so useful for most applications in the electronic industry, because there we need to control the conductivity. We might at a certain stage we might need high conductivity, at a certain stage we might need poor conductivity, and the level of impurities, they control the conductivity. Suppose we introduce a trivalent substance such as boron as impurity in silicon. 3 outermost electrons of boron forge covalent bonds with the 3 outermost electrons of silicon. Remember, silicon has 4 outermost electrons, 3 of them form bonds with the outermost electrons of this trivalent substance, boron in this case. This leaves a vacancy or a hole in the lattice of the semiconductor. I will show you in a moment. At absolute 0 temperature, the energy states where the holes are located are not occupied. So, these states must be above the Fermi energy, which is much closer to the valence band than it is in the intrinsic semiconductors. Let us go back to the silicon structure. 4 outermost electrons for this, 4 for this, and 8 for all of these. This is when it is intrinsic, no impurity. Now, you add an impurity like boron. What happens? 3, 1, 2 and 3, 1, 2 and 3, 1, 2 and 3, these 3 electrons are paired by covalent bonds with the electrons of the outermost shell of silicon. This one is not, there is a vacancy here, because there is no 4th electron in boron. Therefore, the covalent bond cannot be formed. Therefore, this leaves a vacancy for an electron, which we call a hole. It is a missing electron called a hole, and this covalent bond is missing. So, a trivalent impurity like boron creates a p type semiconductor. The semiconductor that is formed by adding a trivalent impurity like boron is called a p type semiconductor. We shall see why it is called p type in a moment. The acceptor energy levels are close to the valence band. At absolute 0, the holes remain unfilled. These holes were here, they remain unfilled here. In a p semiconductor, they remain unfilled. But the electrons from the valence band, because there is very little gap here, they can jump, and when they jump, they leave holes in the valence band. So, when these electrons move, another set of electrons would move here and create more holes. So, the conduction is by holes, and we have seen holes move like positive charges. That is why this semiconductor is called p type semiconductor. However, at temperatures higher than absolute 0, electrons can have energy states above the Fermi energy, with the result that electrons can jump from neighboring silicon atoms to occupy vacancies created by boron. Here was the vacancy created by boron, and because of energy of certain electrons, they can move to this state. That is, they can move from the valence band to the holes here, holes created by the trivalent impurity. Neighboring silicon atoms to occupy vacancies created by boron. In terms of the band diagram, electrons fill the hole in the gap and create holes in the valence band. Since boron is an acceptor of electrons, the semiconductor is said to be a p type, although the electrons are bound in the valence band and cannot move. The holes created there by the presence of dopant can move and respond to the external electric potential. So, they can move, they can cause conductivity. It is possible that at non-zero temperature, a few electrons may jump to the conduction band. As I have been saying, they move to the conduction band and contribute to conduction as minority charge carriers, but the majority charge carriers for conductivity in the p type semiconductors remain the holes. That is, the electrons, when they move, they leave holes, and these holes are produced here. So, the holes the holes move because electrons move, therefore, holes move in the opposite direction. So, in p type semiconductors, the conduction is caused by holes. The gaps, let me show you here also. For example, an electron might move here, a hole is created here. This might move again and say, and a hole is created here. This might move into this hole, a hole is created here. So, the holes can move and they cause the conduction in p type semiconductors. Instead of a trivalent impurity, if we add pentavalent impurity like phosphorus, which has 5 electrons in the outermost shell, to silicon or germanium, the impurity atom is the donor of an unpaired electron to the semiconductor. Why? Because silicon has 4 electrons in the outermost shell, and these 4 electrons can be paired to 4 electrons of phosphorus, but phosphorus has 5. So, there is 1 which is free. So, therefore, phosphorus donates 1 electron to the to silicon or to the semiconductor. Donor is DONOR. So, N, because of this N, the semiconductor so created is called an N type semiconductor, that is 1 electron is donated. The remaining 4 electrons of the impurity atom are bound to the surrounding semiconductor atoms by covalent bonds. Here we have silicon again with 4 outermost electrons, and a phosphorus atom is here, it has 5. So, these 4s are bound by covalent bonds. This one is free, this one is donated, this extra electron, this electron can move, and therefore, the pentavalent impurity donates an electron to the intrinsic semiconductor, and therefore, the semiconductor becomes conducting, and it is called N type semiconductor. In terms of bands, we have conduction band, we have valence bands, and the electrons that were donated, they have energy states very close to the conduction band. So, with a very little energy, they can move to the conduction band and give conductivity to the substance. So, the pentavalent impurities, they make the semiconductor an N type semiconductor, and these electrons have energy states which are close to the conduction band, and therefore, there is a very high probability of these electrons jumping to the conduction band and causing conductivity of the semiconductor. The unpaired electrons donated by the dopant are relatively free to roam around, as I said earlier. Therefore, the donor energy levels are close to the conduction band. At absolute 0, they are slightly inside the Fermi level, because there cannot be any electrons occupying states outside the Fermi energy. The Fermi level is much closer to the conduction band than it is in the intrinsic semiconductors. In the intrinsic, it is in between the energy gap. In the N type, it is close to the conduction band, and in p type, it is close to the valence band. At non-zero temperatures, the electrons can cross Fermi energy and move into the conduction band. A few electrons from the valence band could also jump into the conduction band as in the intrinsic semiconductor. These electrons leave behind holes in the valence band, which contribute to conductivity of the semiconductor as minority charge carriers. Remember, majority charge carriers are electrons which have been donated and which are free, but some electrons from the valence band can also jump and create holes, and then these holes can also contribute to conductivity. Since the majority carriers are negative charges in the case of n type, it is easy to remember that the semiconductor is n type, negative n type. Now, p and n type semiconductors by themselves are not very interesting, not very exciting. When blocks of two materials are placed side by side, nothing much happens. I mean, you have a p type here and n type here, nothing much happens. If you join them, nothing much happens. However, if a single block of a semiconductor is doped with impurities to get p and n type together joined as a p n junction, you see, it is possible that you dope a piece of silicon both with trivalent and pentavalent impurities, and there are p and n semiconductors side by side joined together, then interesting things can happen. This where the place where they are joined is called the p n junction. Very interesting phenomena take place which forms the basis of their application in the development of a large number of electronic devices which we find around us. The simplest of these devices is called a diode. So, electrons from n holes from p, here is n type, here is p type. Here the density of holes is high, here the density of electrons is high. Therefore, the electron density gradient is like this, and the electrons move from high density to lower density. Similarly, holes, here density is higher than here, therefore, they move in the opposite directions. So, electrons move like this in this picture and holes move like this. The meeting of electrons and holes creates a charge depletion layer. You know, when electron meets hole, they cancel each other, and the creates a charge depletion layer. This layer where there is no charge, because electrons and holes they met and the charge becomes 0, and therefore, we have what is known as a depletion layer, a layer where there is no charge. So, accumulation of charges on two sides produces an electric field. Now, if the diffusion from high density to lower density of holes and high density of electrons to low density of electrons, if this diffusion continues, then what happens? We have an accumulation of positive charges here and an accumulation of negative charges here, and an electric field is produced here, or equivalent battery is produced here, and this accumulation deters further diffusion. It stops further diffusion from both sides. The potential difference across the junction may be represented by an equivalent battery, that there is a potential difference or a potential barrier, and the charges cannot move across this barrier. So, when n type and p type are together in a single piece of semiconductor created together, then there is a depletion layer, because there is a diffusion of holes and electrons, and when a hole meets an electron, the charge is neutralized, and we have a depletion layer at the place where there is junction, and then there is accumulation of charges on both sides of this depletion layer, and the barrier created by this charge accumulation does not allow further diffusion across the junction. The symbol of p n junction is shown here. P n junction is shown like this, is a symbol that this triangle is the positive side and this is the negative side. Imagine a p n junction now. The majority carriers in the n semiconductor, where they have a high density, tend to diffuse across the junction, because the electron density on the other side is much lower. Similarly, holes, as I have been saying, from p semiconductor diffuse to the n region across the junction along the density gradient. Initially, the electrons and holes meet and annihilate each other, so that there is a region around the junction which is depleted of charged particles. This region is called the space charge region or the depletion layer. As electrons and holes continue to diffuse across the junction, there is a build up of electrons in the p type and holes in the n type. As I showed you here, there is a accumulation of charges, positive here and negative here, positive in the n region, negative in the p region. Further diffusion of majority carriers from both sides actually stops because of this potential barrier that is created. In the equilibrium that prevails, the potential difference that develops across the junction is called the potential barrier. It is this barrier that charged particles must cross when they have to cross the junction. They must have sufficient energy to overcome the potential barrier. How do they do that? Let us look at this. The potential barrier can be represented by an equivalent battery. As we have said earlier, there is an equivalent battery, that is, potential barrier is like this in this case. And it is important to remember that the height of the potential barrier, which depends on the amount of doping, is part of the design of the diode and is inbuilt at the time of its manufacture. Remember that this P and N are created in the same piece, they are not separate pieces joined together, they are created in the same piece, and the amount of doping will therefore determine the properties of the junction. How much is the potential barrier and how the particles will cross this potential barrier would depend upon the amount of doping. In the silicon p-n junction, the height of the potential barrier is about 0.6 volts. This battery that is created here has a potential difference of 0.6 volts. Suppose now that a p-n junction is connected to an external battery. We have an external battery which is in this way. It was positive here, the external battery has a negative here, and in the same NP junction. The positive end of the battery pushes the holes towards the junction. The holes were not able to move because of the potential barrier, but now this external battery pushes the holes in the p side, and this negative terminal pushes the electrons from the n side. So, the negative end of the battery similarly pushes electrons towards the junction. At low battery voltages, the charges cannot overcome the potential barrier. Potential barrier is about 0.6 volts in silicon. Therefore, unless this voltage goes beyond 0.6, there is no movement of electrons. However, odd electrons, they always have, there is energy distribution, odd electrons can move and they contribute to cross the junction and produce a very weak current through the junction. But this is not important. Important thing is that unless this battery has a potential difference larger than this one, the particles cannot move across the junction. So, this is what is known as forward bias. This pushes electrons on this side, this pushes holes on this side. This is reverse bias. This attracts electrons from this side and holes from this side. So, the whole region is depleted of electrons and holes, and therefore, there is no conduction taking place in this reversed bias. In forward bias, however, if the bias is more than 0.6 volts, there is current going from this side to this side. This is called forward bias, this is called the reversed bias. So, in forward bias, the current flows through the junction when the potential difference is beyond 0.6 volts, and in the reverse bias there is hardly any current which flows through the junction. But as soon as the external potential applied is higher than the potential barrier, that is 0.6 volts, the current suddenly shoots up. You see, up to 0.6 or 0.7 there was no current, very little current, and then it shoots up because now the potential barrier has been surmounted and the electrons can move from the n to the p side, and they contribute to the current, and the current suddenly increases. This is the diode junction characteristics. You see, up to 0.7 volts in silicon, no current, but as soon as the external potential applied is higher than the potential barrier, which in silicon is 0.6 volts, the current suddenly shoots up. You see the characteristics of a p-n diode junction, p-n junction. You see, up to 0.7 volts there is no current, very little current, and beyond that it just shoots up. And this is the reverse current, very small reverse current. You can see it is microamperes, this is milliamperes. So, the current here is really very high compared with the current on this side. The device offers very little resistance, the depletion layer becomes narrower. This depletion layer becomes narrower when there is a forward bias. The electrons now can move from n to p in large numbers, and therefore, the current shoots up. In the reverse case, in the reverse however, very few electrons can move, and therefore, the reverse current is very small. When the polarity of the battery is reversed, say positive here and negative here, then electrons from here are sucked and holes from this here are sucked out. So, that there is no, all the charges have been pulled out, and therefore, nothing can move from this side to that side, no current is there in the reversed wire, and this depletion layer becomes larger or thicker. I will show you here. Yeah, this depletion layer in the reversed bias becomes broader or thicker, here it is narrower in the forward bias case. So, the depletion layer increases in width, the device offers very high resistance to the flow of current. In reverse bias there is hardly any flow of current, therefore, it has very high resistance. Forward bias there is a current flowing freely, and therefore, it is very little resistance. So, in forward bias the resistance of the junction is very small, in the reverse bias the resistance of the junction is very high. When the resistance is very high, the device is said to be reverse biased, or the other way around. When it is reverse bias, then there are charges are pulled on the two sides, and therefore, this whole region is devoid of charges, depletion layer increases in width, and there is hardly any current in the reverse bias case. In the next lecture, we shall continue with this p-n junction, and we shall see how this p-n junction can be used to rectify voltage, that is voltage which is AC, how this AC voltage can be converted into DC voltage. So, we will have half wave rectifier, we will have a full wave rectifier, and then we shall see that the half wave rectifier or full wave rectifier, they are not completely constant, there is slight ripple in them, and we shall study that ripple and full wave rectifier, and then also an important thing, Zener diode in the next lecture.